Question 2. The group 17 elements, chlorine, bromine, and iodine, are non-metals that show trends in their physical and chemical properties. Then part A, describe the trend in the color of group 17 elements down the group. Of course, these colors get darker. Okay, we have that fluorine is a pale yellow-green, you can say yellow-green gas. Then bromine is a brown liquid. You go down iodine, it is a dark gray solid or even black solid. So the color gets darker. We just say color gets darker down the group. As simple as that. Then part B, the group 17 elements can oxidize many metals to form halides. Describe the relative reactivity of elements in group 17 as oxidizing agents. Of course, going down the group, remember, group 17 elements react by gaining one electron. But as you go down the group, the atomic radius keeps on increasing. Okay, that means the attraction between this incoming electron and the nucleus becomes weaker. So it becomes harder to gain an electron. Okay, an oxidizing agent is the one that is reduced. It gets reduced in the process. In other words, it causes another element or compound to lose electrons such that it gains them. You get it? So that is that. Now here, the attraction is weaker. That means it becomes hard for them to receive electrons. So they become weaker oxidizing agents. Okay? But these ones, like chlorine, we can see that the distance is very small in between the incoming electron and the nucleus. So the nuclear attraction here is bigger. So it is easier for chlorine or fluorine to attract electrons. Okay. So that simply implies that they become, these ones up the group, they are stronger oxidizing agents compared to the ones down the group. So we shall therefore say that they are weaker oxidizing agents. They are weaker oxidizing agents or stronger reducing agents. Okay, weaker oxidizing agents down the group. As simple as that. Then Roman 2, chlorine reacts with hot tin metal to form tin 4 chloride. Tin 4 chloride is a colorless liquid at room temperature that reacts vigorously with water to form an acidic solution. So here they are telling us to suggest the type of structure and bonding shown by this and then explain your answer. The fact that it is a colorless liquid at room temperature, that means its melting point is low. Okay, it has already melted because at room temperature, I think that is like 25 degrees C. Okay, so at that 25 degrees C, if it's a liquid, then it has already melted because melting is moving from the solid to the liquid. So these compounds that have low melting points cannot be ionic compounds. They have to be covalent compounds. So we shall say that the structure is simple or molecular. Sometimes we say simple molecular. You can even just say that simple molecular structure. Then explanation, because of low melting point. In the question here, you are not seeing the melting point that it is given, but the fact that it is a liquid at room temperature, then it has already melted. Okay, and then let's look at the bonding. So the bonding here is going to be, of course, covalent. The bonding is covalent. Why? Because this one is easily hydrolyzed, because it is hydrolyzed. As simple as that. Then part C, they are saying that the group 17 elements form soluble halides with sodium. And then they are saying that Roman 1, describe what is seen when dilute silver nitrate is added to sodium bromide followed by aqueous ammonia. Now, of course, we are going to see this one here. Because it is a soluble halide, you are going to have sodium bromide here, aqueous. So it dissolves and then it gives the sodium ions and then the bromide ions. You see that? Then now from here we have silver nitrate. Okay, silver nitrate here is going to break down to give you, this one is also soluble salt. So silver ions and also nitrate ions. Then these two, this one and this one are going to react. So we have silver ions, then plus the bromide ions. Then you are going to get silver bromide, which is a cream precipitate. Okay, precipitate. So that's why I'm putting here a solid. Now we are going to see that cream precipitate, but then what is going to happen is that chlorides, for the chlorides, they are soluble in aqueous ammonia and also in concentrated ammonia. Then when it comes to the bromides, they are partially soluble in aqueous ammonia. Sometimes they even say insoluble in aqueous ammonia, but in concentrated ammonia, they are soluble. And then when we go to iodides, iodides are soluble in aqueous, actually iodides are insoluble in aqueous ammonia and also concentrated ammonia. Let me show you something here. Now this is group 17. So group 17 is here. We are going to look for that table which talks about the solubility. Yes, it is here. Look at this. We have bromides, cream precipitate, remains insoluble, but it is partially soluble. Okay, it has what we call the KSP, the solubility constant. In A level, you will learn about that one. So it is partially, when you mix something like partially soluble, even these ones we say are insoluble. Sometimes if they have that KSP, then there is something small that goes into the solution. Okay, so in concentrated ammonia, then it is soluble. But then for iodides, it's a yellow precipitate. It is insoluble in aqueous and also insoluble in concentrated ammonia. But when you look at the chlorides, for them, they are soluble in dilute and also in concentrated ammonia. Okay, so that is what I wanted you to see. So we shall say cream precipitate partially dissolves in aqueous ammonia. And if you say maybe insoluble in aqueous ammonia, they can also give it to you. So that is that. Roman 2, sodium chloride reacts with concentrated sulfuric acid to form hydrogen chloride and sodium hydrogen sulfate. Now, when you look at this sulfuric acid, it has lost what? A hydrogen to give you the ion hydrogen sulfate. So that means since it has lost a proton here, then it acts as an acid. Okay, so this is an acid-base reaction. Okay, explain the difference between the reactions of concentrated sulfuric acid with sodium chloride and with sodium iodide. Your answer should refer to the role of sulfuric acid in each reaction. So, in this reaction here, the role of sulfuric acid is, actually it acts as an acid. Okay, so this sulfuric acid acts as an acid with the chloride. Okay, but then when we go to the iodide, sulfuric acid acts as an oxidizing agent. Remember, going down the group, these halides become more of reducing agents. They become stronger reducing agents and weaker oxidizing agents. So sulfuric acid here is a stronger oxidizing agent compared to the iodide here. So that's why the hydrogen, this is HCl. For the hydrogen iodide, this one is broken further, okay? And even these bond energies here, as you go down the group, they become weaker. So it is easier to break this one down to iodine, okay? So here sulfuric acid acts as an oxidizing agent, okay? With the iodide, to produce for example, iodine. It can produce sulfur dioxide, it can produce sulfur, it can produce hydrogen sulfide. Okay, this is what happens for iodine. Let me just put it here. So you have, let's say, sodium iodide. So sodium iodide reacts with sulfuric acid. First, that reaction is acid-base. You are going to get hydrogen iodide plus sodium hydrogen sulfate. But this one here easily breaks down, okay? Easily breaks down. So we shall have hydrogen iodide, then plus the sulfuric acid. So this one is now a stronger oxidizing agent compared to this one. So we are going to have iodine here, then plus we can have sulfur, we can have hydrogen sulfide, we can have sulfur dioxide, then plus water, okay, for all of them. So I'm not going to waste time by balancing, okay, but that is what happens, okay, all of these three. So you can just get this one, maybe this one, or with that one. So those are all the possible outcomes of this reaction here. So you can see here that we have -1, but then this one becomes 0, okay. Sulfur here, the oxidizing agent, the oxidation number is of course 0, and then here it is +6. So this one has been reduced, right? So if it has been reduced, and then this one, there is increase in oxidation state, then it has been oxidized, okay? This one is reduced. So it is a redox reaction. So the role of sulfuric acid here is to act as an oxidizing agent, all right? But this one is not broken any further. For it, chlorine here is a stronger oxidizing agent compared to sulfuric acid. So that is that. Then part D, the hydrogen halides are useful reagents in organic and inorganic reactions. Roman 1, describe and explain the trend in the boiling points of hydrogen halides, the HCl, HBr, and hydrogen iodide. Here the boiling point, because these are molecules, the boiling point has to increase down the group, because for these molecules, we look at the number of electrons. The more the number of electrons, okay, the stronger the van der Waals forces of attraction. So I will say boiling point increases down the group. Why? This is because of the increasing number of electrons, thus increasing the strength, because for boiling point you have to talk about the strength of the intermolecular forces. okay, in there. So the strength of the van der Waals forces, or the ID forces, okay, between molecules. You can put ID, instantaneous dipole-induced dipoles, okay? So that is that. Then Roman 2, describe and explain the trend in the thermostabilities of the halides. Thermostabilities, how do these ones break as you heat? So it becomes very, very easy to break these halides as you go down the group. Why? You have this halide here, very big, and then the distance between that and the shared electrons here with the hydrogen is big. So compared to this one, maybe for chlorine, the distance here is small. So the shorter the bond, the stronger it is. Then the longer the bond, the weaker it is. Why? Because there is weaker attraction between this nucleus and the electrons here. You see that? So we are going to say that thermal stability decreases down the group. Thermal stability decreases down the group. Okay, why? The hydrogen to halogen bond is weaker. Down the group. Why? Let me add an explanation for this one here, but these are the 2 points that you're supposed to put. There is decreased nuclear attraction to the bonding electrons, of course by the nucleus, okay, in this bond, okay, due to stronger shielding. Remember, you are adding shells and shells. So that stronger shielding of these electrons by these inner electrons pushes these electrons far away, and then the attraction becomes very weak. Okay? So because of the stronger shielding and bigger ionic, okay, radius. So that is that. These are the ones which contribute to the weakness of that bond. So that is that. Part E, Lucas's reagent is a mixture of HCl and zinc chloride. Primary, secondary, and tertiary alcohols can be distinguished by their reaction with Lucas's reagent. Alcohols react with HCl in Lucas's reagent to form halogenoalkanes. So zinc chloride acts as a homogeneous catalyst for these reactions. Explain the meaning of the term homogeneous catalyst. Of course, this is the one which is in the same phase. Homo means one, okay? One phase, so same, okay, same phase as reactants, as simple as that. And then pentan 3O reacts slowly with HCl to form a secondary halogenoalkane. Complete the equation for this reaction using the structure formulae. Okay, now we are adding HCl, right? HCl here, and then there is a substitution. It's because we are forming a halogenoalkane. So where there is OH, you put Cl. So we can have C2H5, then CH, then we can have Cl, then C2H5, like that. Okay, then Roman 3, the fastest reaction shown by Lucas's reagent is with the tertiary alcohol. Draw the structure of the tertiary alcohol, that is an isomer of pentan 3-ol. Now, when we check pentan 3-ol, it is CH3, CH2, then C, then here I can have the OH on the third carbon, add a hydrogen here, then here we shall have CH2, CH3. Now, an isomer can be, if it is a tertiary one, so it can be chain isomerism. I can cut this one here, and then I put it on this carbon here. So when I do so, this hydrogen, of course, now will go to that one there. So we shall have CH3, okay, here, CH3, then C, then we shall have this CH3 here has come down here. It has substituted with that hydrogen, so we shall have a CH3 here. Then there is an OH here, and then here we shall have a CH2, CH3. So we are having this alkyl group, the ethyl, then the methyl, and then the methyl. So those are 3 alkyl groups which are on this carbon atom that has gotten this OH bond. Okay, that has gotten that functional group. So it is a tertiary alcohol. Okay, then Roman 4, tertiary alcohols tend to react with Lucas's reagent using the same mechanism as in their reaction with HCl. Okay, suggest the type of reaction shown by tertiary alcohols with Lucas's reagent. This is just a substitution reaction. Substitution reaction. We have seen that they form what? Halogenoalkanes. It is here alcohols react with HCl in Lucas's reagent to form halogenoalkanes. That means where there is the OH, we have substituted with the what? A halogen. As simple as that. So that is substitution reaction.